Assalamualaikum and good day everyone. Today we are going to look into chapter 4, signal characteristic and conditioning. Basically, in this chapter we will learn on the characteristic of the signal and also the condition where we need to consider for the signal. Okay. So this chapter will cover several subtopics such as concepts and various type of signal. Then we will look into signal mathematical properties, principle of signal conditioning. We will also look into the use of different signal conditioners such as filters and amplifiers. And finally, we will also learn the basic concept of ADC and DAC. Okay. Actually, ADC is referring to analog to digital converter, while DAC is digital to analog converter. Okay. First, we will look at the concepts and various types of signal. What is signal? Okay. As stated here, signal is physical or virtual quantity that varies with time or space or any other independent variable or variables. Alright. So basically, in general, a signal is a quantity that carries information. Signal can take many different forms, okay, including electrical, acoustic, optical, or maybe electromagnetic wave. For example, when we say hello on the telephone, the word hello will be converted into signal by the telephone transmitter, transmitted by wires to the receiving telephone. Then it will reconvert the signal into sound by the receiver. So, graphically, the signal can be represented by the independent variable which is represent the horizontal axis or x-axis, and the dependent variable that represented by y-axis. Mathematically, a signal is a function of one or more than one independent variables. We will look at several examples of signal. In an electrical system, the physical variables of interest might be voltage, current, amount of charge, or many more. However, in mechanical system, the variable of interest might be the position, velocity, mass, volume of various objects. From financial aspect, a signal might include the price of stock, commodity or option, an interest rate or an exchange rate. While in communication system, a transmitter encodes a message into a signal which is carried to a receiver by the telecommunication channel. There are two types of signal, analog signal and also discrete time signal. Basically, analog signal are continuous waveform that vary in amplitude and frequency over time. The digital signal, on the other hand, are discrete, representing information as a series of binary value at discrete point in time. let's look at the example of discrete time signal or digital signal. The signal is represented as a sequence of discrete samples, with each sample representing the amplitude of the audio at a specific point in time. So we have three type of digital signal here. Okay, first is the true representation. This describes a digital audio signal that can be represented as a sequence of discrete data at a specific point in time. Next, we also have the waveform representation. Okay, this signal describes a digital audio signal that can be represented as a waveform, which is a graphical representation of the signal that shows how the amplitude of the signal change over the time. The waveform is created by connecting the dot on the graph with line, that creating a continuous line that are representing the audio signal. So the resulting waveform represents the shape of the audio signal over time, showing the changes in amplitude and frequency of the time. Next, we have the graphical representation. A digital audio signal can be graphically represented as a sequence of discrete points, with each point representing a sample of the audio signal. The amplitude of the audio signal is plotted on the y-axis, and the time at which each sample was taken is plotted on the x-axis. The resulting graph is a series of dots connected by line, with each dot representing a sample of the audio signal. We will go into signal mathematical properties. Okay. There are various signal waveforms such as static, dynamic, and also non-deterministic waveform. Each of the type of waveform can be represented by mathematical equation as shown here. What is non-deterministic waveform? We will look at it in the next slide. Here are several types of signal that can be categorized based on deterministic variable and non-deterministic variable. What is deterministic variable? Right? So a deterministic variable is a variable which the behavior can be predicted with certainty using a mathematical equation or function. In the other word, a deterministic variable has a predictable pattern or behavior that can be precisely described by a mathematical model. For example, we have here a sinusoidal wave or sinusoidal signal. We also have ramp and step. So they can be described by a mathematical equation which presented in the slide before, and the behavior can be predicted with certainty. Let's look at non-deterministic variables. Okay, this is a variable which the behavior cannot be predicted with certainty or using a mathematical equation or function. Or we can say that this variable has a random or unpredictable pattern or unpredictable behavior that cannot be precisely described by mathematical model. For example, we have white noise or random telegraph signal. They are non-deterministic signal. This is due to their behavior that is random and cannot be predicted with certainty. Actually, this difference has important implication for the analysis and processing of dynamic signal, as it determines the types of mathematical models and techniques that can be used to analyze and process the signal. Okay, let's look at this example on electrocardiogram ECG signal. So, in terms of the difference between deterministic and non-deterministic variable, ECG signal are generally considered to be deterministic signal. This is because the electrical activity of a normal heart should follows a predictable pattern with each heartbeat producing a characteristic waveform that can be described mathematically. This waveform consists of series of deflections including the P wave, QRS complex and T wave that represent the different phases of the cardiac cycle. Alright. However, it can be non-deterministic signal, okay, because this is due to certain medical conditions such as heart block that can cause irregularities in the ECG waveform that are not predictable based on normal cardiac function. Okay, the vibration acceleration signal during one cycle of engine operation with timing for one cylindrical typically has a periodic waveform with a series of peak and valleys that correspond to different phases of combustion cycle. The waveform can be divided into four main phases such as ignition, opening of exhaust valve, closing inlet valve, and also closing the exhaust valve. The timing of these phases can vary depending on the engine design and operating condition. In a 4-stroke engine, each phase corresponds to one stroke of the piston, while in 2-stroke engine, some of these phases may be combined. So overall, the vibration acceleration signal during one cycle of engine operation with timing for one cylinder will provide important information about the performance and also the condition of the engine. Okay, this information can be used to diagnose problems such as misfires, imbalance, or maybe excessive wear of the component in the engines. Next, we will look at the faulty bearing detection. This faulty bearing detection can be performed using noise signal analysis in the time domain. So when a bearing is faulty, it may produce irregular or unpredictable vibration that can be detected through a noise signal analysis. Okay, in the time domain, a healthy bearing signal will generally exhibit a consistent and smooth waveform with a low level of amplitude. This waveform will typically be periodic and repeat at a regular interval, that indicating that the bearing is functioning properly and producing a consistent vibration. However, for a faulty bearing, the signal will often exhibit irregularities, okay, in the time domain, such as sudden spike, okay, if you look at here, and drops in amplitude, or a change in the shape or duration of the waveform. These irregularities can indicate problems such as damage to the bearing or the presence of other mechanical issues, and may also be accompanied by audible noise such as squeaking or grinding. So it may help the engineer to identify what are the problem of the engine. Okay, there are some sample of signals from different sources. You may look at this later. Next, we will go into the principle of signal conditioning. In the real world, signal conditioning is usually used to improve the quality of signals that are generated by sensor or other transducers before they are processed by measurement or control system. Okay. The signal conditioning stage usually involve a variety of techniques such as amplification, filtering, linearization, and also isolation. This process is important to prepare the signal for further processing. Okay, so here we are going to look into an example of how signal conditioning might be used in real-world application. First, we have here signal source. A sensor such as temperature sensor or pressure transducer is used to measure a physical parameter and generate an analog signal. Okay, the analog signal from the sensor is processed using various signal conditioning such as amplification or filtering. Okay, this process is used to improve the signal quality and remove any unwanted noise or maybe interference. The conditioned signal is then converted from an analog signal to digital signal using an analog to digital converter, ADC. Next, the digital signal is then passed to the driver software, which communicates with measurement or control system and then convert the signal to a format that can be used by the system. Finally, the digital system is processed by the application software. Okay, here they analyze the data and provide the user with information about the physical parameter that are being measured. Okay, so overall, signal conditioning is an important part of many measurement and control system because it helps to ensure the signal are accurate, reliable, and also consistent over the time. So by carefully selecting and applying the appropriate signal conditioning techniques, engineers can improve the quality and usability of signals in a wide range of applications. Okay, electrical engineers use operational amplifiers, op-amps, resistors, capacitors, diodes, transistors to perform mathematical operations such as multiplication or division. In multiplication or division, by using resistor, they are used to create voltage dividers and operational amplifiers in non-inverting or inverting amplifier configuration. Engineer can perform multiplication and division operation on analog signal. They also use addition and subtraction. By using operational amplifiers in summing amplifier configuration, they can add or subtract multiple analog signal. Then they also have absolute value. Using diodes and operational amplifiers, engineers can create circuit that perform the absolute value function. This function will give the magnitude of a number without regard to its sign, whether it is positive or negative. Next, by using diodes and operational amplifiers, we can also create circuit that perform the natural logarithm function, which is useful for a variety of application, including signal and also control system. For filters, by using capacitors and resistors in various configuration, we can create filter that pass certain frequency and while blocking others. For example, a low pass filter can be used to follow low frequency signal to pass while blocking high frequency signal at the same time. So overall, these mathematical operations are essential to the design and operation of many electronic systems. So we need to carefully select and configure the appropriate electronic components because we can create circuit that perform this operation with high accuracy and reliability, at the same time allowing for a wide range of application in many different fields. As a summary, signal from detector or sensing stage has to be there are several common signal conditioning such as amplification, attenuation, filtering, differentiation, integration, linearization, combining a measured signal with reference signal, and also converting between electrical parameters or known as VIR. But here we are going to pay attention on the three most common signal conditioning. Okay, amplification is the process of increasing the amplitude of a signal. In signal conditioning, operational amplifiers are usually used to amplify the signal. So by adjusting the feedback resistor in an op-amp circuit, we can create circuit that amplify signal by a desired amount. Amplification is useful in many application such as in audio amplifiers or instrumentation amplifiers, or maybe signal processing circuit. While attenuation is the process of reducing the amplitude of a signal. Okay, the voltage dividers are usually used to attenuate the signal by adjusting the resistor value in a voltage divider circuit. We can create circuit that attenuate signal by our desired amount. So attenuation is useful in reducing the amplitude of a signal to a level that can be safely measured or processed by other circuitry. So next, we have filtering. Filtering is the process of selectively removing or attenuating certain frequencies in a signal. Filters are usually used to remove unwanted noise or interference from a signal, or to extract certain frequency component of a signal. Okay, there are many types of filter, such as low pass filter, high pass filter, band pass filter, and also notch filter. Filters are used in audio amplifiers, power supplies, and communication systems, among other applications. Okay. Next, we will look at the amplification and its general characteristic. Okay. An audio power amplifier is an electronic device that increase the power or amplitude of an audio signal to drive a speaker or other type of load. The primary function of a power amplifier is to convert a low power, high impedance signal from a preamplifier or signal source into a high power, low impedance signal capable of driving a loudspeaker. In the signal conditioning, we have the operational amplifier, op-amp. So these operational amplifiers take small voltage and make them much larger. So there are golden rules for op-amp with negative feedbacks. The first one, no current flows into either positive or negative inputs. The second one, the positive and negative input. Now we are going to look into the inverting and non-inverting amplifier. Inverting and non-inverting amplifier are two common configurations of operational amplifier, or we known as op-amp circuits. So in an inverting amplifier, the input signal is applied to the inverting input terminal of the op-amp that is connected to the feedback resistor RF and the output of the op-amp. The non-inverting input terminal is connected to ground or a virtual ground. So the output of the op-amp is connected to the inverting input terminal through the feedback resistor. The gain of the amplifier can be determined by the ratio of the feedback resistor RF to the input resistor R1. So we can say that the output signal is the amplified and inverted version of the input signal. In a non-inverting amplifier, the input signal is applied to the non-inverting input terminal of the op-amp that is connected to feedback resistor and the output of op-amp. The gain of the amplifier is determined by the ratio of the feedback resistor RF to the input resistor R1. So the output signal is the amplified and non-inverted version of the input signal. Okay, here we have the unity follower. A unity follower, also known as a voltage follower. This is a special case of a non-inverting amplifier where the output voltage follow the input voltage without any amplification or attenuation. The gain of a unity follower is equal. That's why the name is the unity follower. In a unity follower, the input signal is applied to the non-inverting input of op-amp and the output is connected directly back to the input terminal. Okay, a feedback resistor is not used in this configuration because the op-amp is configured to have a high input impedance and a low output impedance. Okay, this unity follower is used in application where the signal needs to be isolated from the load, where a high input impedance at a low output impedance are required, or where buffering is needed to drive a low impedance load. For example, the application where unity followers are used include the buffer amplifiers, impedance matching circuits, or maybe the voltage regulator. Okay, here we have the summing amplifier. A summing amplifier is an operational amplifier circuit that can add multiple input signal and produce a single output signal. The output signal of the summing amplifier is the sum of this input signal scaled by individual gain factors. In a summing amplifier, multiple input signals are applied, okay, to the inverting or non-inverting input terminal of the op-amp through individual input resistor. Okay, we have R1, R2, and R3. The other end of this input resistor are connected together at a summing junction. So the output voltage of the summing amplifier is equal to the sum of the input voltage multiplied by their corresponding gain factor. Okay, for example, summing amplifiers are usually used in audio mixers where multiple audio signals are combined into a single output signal. Okay, next we have integrator. Integrator is an operational amplifier op-amp circuit that perform mathematical integration on an input signal. The output voltage of the integrator is proportional to the time integral of the input voltage. In an integrator circuit, the input signal is applied to the inverting input terminal, the negative, of the op-amp through a resistor. And a capacitor is connected between the inverting input terminal and the output of op-amp. The resistor and capacitor will form a low pass filter, allowing low frequency components of the input signal to pass through while blocking the high frequency component. The output voltage of this integrator is proportional to the integral of the input voltage, which make it more sensitive to low frequency variations. Okay, typically integrator are used in applications such as waveform generation, frequency modulation, or signal processing. Next, we have a differentiator. Okay, a differentiator is an op-amp circuit that perform differentiation on an input signal. The output of the differentiator is proportional to the rate of change of the input voltage with respect to time. In a different differentiator circuit, the input signal is applied to the inverting input terminal, negative, of the op-amp through a capacitor. And a feedback resistor is connected between the output and op-amp and also the inverting input terminal. This capacitor will act as a high pass filter that allow the high frequency components of the input signal to pass through while blocking the low frequency components. The output voltage of the differentiator is proportional to rate of change of the input voltage, which make it more sensitive to high frequency variations. Typically, differentiators are used in applications such as waveform shaping, pulse detection, and signal processing. For example, a differentiator circuit can be used to differentiate a pulse signal, to detect the arrival time of the pulse, or to differentiate a sine wave in order to produce a cosine wave. In this slide, we have attenuation. A voltage divider network is a typical of electrical circuit that is used to divide a voltage into smaller values. It consists of a series of two or more resistors connected in a series between a voltage source and ground. So the voltage across each resistor is proportional to the resistance value and the total voltage of the circuit. Why we need to reduce the output level? For example, in sensor circuit, the output voltage of a sensor may be too high to be processed by other circuit components. Therefore, a voltage divider can be used to scale down the output voltage of the sensor to a level that can be handled by an ADC, analog to digital converter, or other processing circuitry. So, the simplest voltage divider network consists of two resistors connected in series. The voltage divided equation for this circuit is V out equal to V in times resistance 2 divided by the sum of total resistance, where this is the input voltage, R1 and R2 are values of the resistor, VO is the output voltage. By adjusting the value of R1 and R2, the output voltage can be varied to any desired value between 0 and the input voltage. Okay, next we have filter. Filter is the network used to attenuate certain frequencies but allow others without attenuation. Filter consists at least one pass band, which is a band of frequencies that the output is approximately equal to input, and attenuation band that the output is equal to 0. Cut-off frequency is the frequencies that separate the various pass and attenuation bands. Important characteristic of filter networks is its construction that make use of purely reactive elements. There are two types of filter. One is passive filters, the other is active filters. Next, we have filter. There are two types of filter, passive filter and active filter. Passive filter only use passive circuit components such as resistors, capacitors and inductors, while active filter use active elements like operational amplifiers in addition to passive elements like resistance, capacitance and inductance. Both of passive and active filter can be classified as follows. They are low pass filter that deliver low frequencies and eliminate high frequencies. Secondly, high pass filter that send on high frequencies and reject low frequencies. Next, there is band pass filter that pass some particular range of frequencies, discard other frequencies outside that band. And lastly, we have band stop filter that stop a range of frequencies and pass all other frequencies. So as a revision, we will look at this figure. So the ideal response of a low pass filter is shown in figure A. Low pass filter. This gain is a constant over a frequency range starting from 0 to cut-off frequency. The output of any signal having a frequency greater than this cut-off frequency, FC, will be attenuated. For example, there will be no output voltage for frequencies greater than the cut-off frequency, FC. Therefore, the output will be available from 0 to FC with a constant gain, and is 0 from FC and forward. So the characteristic of high pass filter are shown in figure B. Okay, this is a high pass filter. So this high pass filter has a zero gain starting from 0 to a frequency FC. The cut-off frequency. Okay, above this cut-off frequency, the gain is constant and equal to let's say A. Therefore, the signal of any frequency beyond FC will reproduce with a constant gain or with a frequency from 0 to FC that will be attenuated. Next, we have the band pass filter. So this is a band pass filter. It reproduces signal falling between FC1 and FC2, while the signal between 0 and FC1 and frequencies greater than FC1 are attenuated. So there is an output corresponding to signal having the frequencies between FC1 and FC2, but no output for signal having frequency below FC1 and above FC2. So this filter pass a band of frequencies. This is the characteristic of band stop filter. This filter attenuates a particular band of frequency from FC1 to FC2, while passing all frequency between 0 to FC1 and FC2 onward. So this filter is also called a notch filter. Figure E shows the characteristic of all pass filter. So in this filter, all frequencies are passed without attenuation. So, the important feature of this filter is that it provides a predictable phase shift of frequencies of different input signal. These filters are mostly used in communication. Okay, next we will look at this passive filter. First, we have a low pass filter. It blocks high frequencies and pass low frequencies. The ideal LPF is the signal above the cut-off frequency are simply rejected. In terms of resistor and capacitor, cut-off frequency is given by this equation, and gain is given by this equation. At low frequencies, the capacitive reactance is very high. Therefore, the capacitor circuit acts like an open circuit. At very high frequencies, the capacitive reactance is very low. Therefore, the output voltage is very small compared to input voltage. For high pass filter, in passive filter, it passes high frequency and blocks or rejects the low frequencies. The ideal HPF stated that the signals below cut-off frequency are simply rejected. In terms of resistor and capacitor, cut-off frequency is given by, and gain is given by this equation. At low frequencies, the gain is small. Therefore, the output voltage is small as compared to input voltage. As the frequencies go high, the gain approach unity. Next, we have a band pass filter for passive filter. It blocks frequencies below a low limit and above a high limit, while passing frequencies between the limits. It can be constructed by cascading LPF and HPF. At frequencies below the pass band, PPF behave like HPF, but while above the pass band frequencies, the BPF will act like LPF. In pass band, the BPF circuit is almost as a resistive network. Thus, gain is given by this equation. For the lower cut-off frequency, we can calculate based on the given equation, while for the upper cut frequency, this is the equation. Then we have band stop filter for passive filter. It blocks a specific range of frequency. It can be realized but not very effective one. Simple RC combination, also known as notch filter. The circuit is called twin T filter. Twin T BSF at the very low and high frequency, the gain is almost unity. But between the two, there is a frequency where the gain becomes 0. The frequency is known as notch frequency, is given by this equation. Next, we have active filter. Active filter. Generally, the impedance are used in the inverting amplifiers using operational amplifiers. Basic relationship can be used to obtain the desired filter section is showing in this equation. The voltage can also be amplified. Then we will look at the active filter and its advantages over the passive filter. So first one, inductors can be avoided. Passive filter without inductors cannot obtain a high Q, which is the low damping, but with them are often large and expensive, basically at low frequencies, may have significant internal resistance and may pick up surrounding electromagnetic signals. Next, the shape of the response, the Q, quality factor, and the tune frequency can often be set easily by varying resistors. In some filters, one parameter can be adjusted without affecting the others. Variable inductance for low-frequency filters are not practical. The third one, the amplifier powering the filter can be used to buffer the filter from the electronic components it drives or is fed from, variation in which could otherwise significantly affect the shape of the frequency response. So, electronic filters are important for separating signal from noise in end measurement. Okay, they are popular filters such as low pass, high pass, and band pass. The passive filter will use RC or LR. The active filter will use op-amp. So, this is the signal conditioning for RC filter. An RC filter is a type of filter that use a combination of resistor R and the capacitor C to filter the signal. So the basic configuration of an RC filter consists of a resistor in a series with a capacitor. The input signal is applied across the capacitor and the output is taken across the resistor. Okay, here we have a low pass RC filter, which is a circuit that pass a low frequency signal while attenuating high frequency signal. So this filter is typically implemented by placing a capacitor in series with the input signal and a resistor in parallel with the capacitor. Okay, the cut-off frequency of the filter is determined by value of the resistor and capacitor. Signal with frequencies below of the cut-off frequencies pass through the filter largely unattenuated, while signal with frequency above the cut-off frequency are attenuated. Next, in the high-pass RC filter is a circuit that pass high-frequency signal while attenuating low-frequency signal. This filter is typically implemented by placing a resistor in series with the input signal and a capacitor in parallel with the resistor. Okay, the cut-off frequency of the filter is again determined by the value of resistor and capacitor. Signal with frequencies above the cut-off frequency pass through the filter largely unattenuated, while signal with frequency below the cut-off frequency are attenuated. Okay. Next, we have a band pass RC filter. Okay, this is a circuit that pass signal within a certain range of frequency, while attenuating signal outside that range. This filter is typically implemented using a combination of a high pass and low pass RC filter. The output of the high pass filter and the low pass filter are then combined to form the band pass filter. The center frequency and bandwidth of the filter are determined by the values of the resistors and the capacitors in the high pass and low pass filters. Okay, if you need more detail about filter design and analysis, you can scan this barcode and you can explore. Okay, so this is the attendance for today's class. So please make sure that you fill up the form, and thank you for your time.